Forces on charged particles, magnetic fields, past paper questions. Revised Higher 2014, question 26. Explain how particle accelerators such as the Large Hadron Collider at CERN are able to accelerate charged particles and deflect charged particles. Well, in part 1, in order to accelerate charged particles, we use an electric field. An electric field exerts a force on a charged particle causing it to accelerate. In part 2, in order to deflect the charged particles, we use a magnetic field. So a magnetic field is used to deflect or change the path of a charged particle. In the Revised Higher 2013 paper, we see an example of a particle accelerator called a cyclotron. A cyclotron is used in a hospital to accelerate protons, which are then targeted to kill cancer cells. A cyclotron consists of two D-shaped hollow metal structures called Ds, and they are placed within a vacuum. The diagram shows a cyclotron viewed from above. Protons are released from rest at point R, as here, and they are accelerated across the gap between the Ds by a voltage of 55 kilovolts. So 55 kilovolt supply is used to accelerate the particles between R and S. So that's our electric field. Protons are released from rest at R and are accelerated across the gap between the Ds by a voltage of 55 kilovolts. We're asked to show work done on the proton as it accelerates from R to S, the speed of the proton, what the direction of the magnetic field is going to be, and also explain why an alternating voltage is used in the cyclotron. So let's look at the first part. So in the first part, we're asked to show that the work done on a proton as it accelerates from R to S is equal to 8.8 times 10 to the negative 15 joules. So here the equation we're going to use for part 1 is W is equal to QV. We can get the charge on a proton from the datasheet, and that's 1.6 times 10 to the negative 19 coulombs. And we know the potential because it's given in the questions, 55 kilovolts, which we convert to volts. Multiply those two together, and we get a value of 8.8 times 10 to the negative 15 joules as required. In part 2, we're asked to calculate the speed of a proton as it reaches S. We did this in our previous videos where we were looking at electric fields. We know that in an electric field, work is done in moving the charge, and if that charge is going with the field, then the work done is equal to the kinetic energy. So W is equal to 1/2 mv squared. Now it's perfectly fine at this point to substitute in, or if we want to we could do a rearrangement here. But in order for us to be able to do this question, we need to know the mass of a proton. So the mass of a proton from the data sheet at the front of the paper is 1.673 times 10 to the negative 27 kilograms. So let's substitute that in. 8.8 times 10 to the negative 15 is equal to 1/2 multiplied by the mass of a proton, 1.673 times 10 to the negative 27 multiplied by v squared. Rearrange, v squared is equal to 8.8 times 10 to the negative 15 divided by 1/2 multiplied by 1.673 times 10 to negative 27. Now obviously v is equal to the square root of v squared, so v is the square root of all of this together, and that gives us a value of the velocity to be 3.2 times 10 to the 6 meters per second. So we're going very fast here. Okay, in part B, we're asked to determine the direction of the magnetic field. We're dealing with a positive particle here, so we can use the left-hand rule. So in the left-hand rule, if you're pointing at the screen, your thumb is pointing up and your second finger is pointing to the right. Now we need to make sure we align this with everything that's going on. So we can see within the motion, as the particles accelerate across the graph R to S, it's moving in an upwards direction. So our thumb stays pointing up. Our second finger shows the direction of the movement of the positive particle, and that's in the right alignment as well because that's moving left to right, which means our field must be moving into the page. Into the page. Now, because we're looking at the cyclotron from an upwards position as if we're looking down, we'd also accept down. In the next part, we're asked to explain why an alternating voltage is used in the cyclotron. Well, if you think about it, remember in the electric field theory, if we change the polarity, if we change the direction of the electric field, we're going to change the direction of the particle. And that's really what we want to do. So an AC voltage is used in order to change the direction of the force on the protons across the gap. Because in one cycle, the protons are going left to right, as we saw R to S, but then as it moves to the top, they've got to move from S to R. So we need to change the direction of the force on the protons across the gap as they change direction going around. Now, because they're going around and then going around and around and around, that electric field must change direction repeatedly as the direction changes repeatedly. So the direction of the protons as they cross the gap must keep changing. As we see in AC. In this question, we're looking at probably the most famous of the particle accelerators. We're looking at the Large Hadron Collider. And within the Large Hadron Collider, beams of hadrons are travel in opposite directions inside of a circular accelerator, and then they collide. The accelerating particles are guided around the collider using strong magnetic fields. The diagram shows the proton entering the magnetic field. In which direction is the proton deflected? So again, we can use the left-hand rule here. So you have your left-hand rule, remember, left-hand rule for a start. Your fingers, first finger is pointing towards the screen, your thumb is pointing up, and your second finger, your middle finger, is moving to the right. So our second finger is the direction of the proton, so I move my hand to the left. So now my middle finger is pointing towards the screen, my thumb is pointing up, and my first finger is pointing to the left. However, my first finger shows the direction of the field, so I need to flip my hand over. And as I flip my hand over, I can see that my second finger, middle finger, is pointing in the direction of the proton. My first finger is pointing in the direction of the field, which is going to the right. And then my thumb is pointing down. So the direction the proton is deflected is down. In the next part of the question, we're told that the neutron is classified as a hadron. Yes, it is. Explain why neutrons are not used for collision experiments in the LHC. So we use protons in the collision. Why not use neutrons? Well, fundamentally, neutrons have no charge. And because they have no charge, they cannot be accelerated. They can't be moved because they don't experience a force. So they cannot be accelerated by the electric field and cannot be deflected by the magnetic field. Okay, so this is from the revised higher specimen paper, and so a page from How Things Work. Scientists have created several working prototypes of a corona discharge cooler, which can be silently but effectively cool the microprocessor within a computer. So we have a high voltage supply, a corona electrode, and the corona electrode collector, and neutral air particles, as well as ionized charged particles. And we see the positively charged ionized particles moving to the right. The corona discharge cooler works in the following manner. A strong electric current is created at the tip of the corona electrode, that's here, which is placed on one side of the microprocessor. This causes the oxygen and nitrogen molecules in the air to become ionized, that is positively charged, and create a cloud or corona of charged particles. Placing a negative electrode at the opposite end of the microprocessor, that's here, causes the charged ions to accelerate towards the electrode, colliding with neutral air molecules in the way. So the charged particles are moving and they collide with the neutral air particles. During these collisions, momentum is transferred from the ionized gas to the neutral air molecules, resulting in a movement of the gas towards the collector electrode. The advantages of corona-based coolers are there are no moving parts, it operates with near zero noise level, and has a very low power consumption of 0.1 watts. Here are our questions. Describe how the gas molecules become ionized. Explain why the charged ions accelerate towards the collector electrode. The potential difference between the electrodes is 1 kilovolts, assuming that the field between the electrode is uniform and the charge on each ion is 1.6 times 10 to the negative 19 coulombs. Calculate the work done in moving one ion between the electrodes. Calculate how many ions are created each second, and explain how the device cools the microprocessor. So you can have a shot at this yourself if you pause the video, and on the next slide we'll explain the answers. Okay, so part one of the question. Describe how the gas molecules become ionized. So the electron orbits around the nucleus of an atom. There's an equal number of electrons as there are protons in a stable atom. In order to ionize the gas, an electron must be added or removed from an electrode. In this case, an electron is removed. By the electrode. We know then electrons being removed because we are creating positive ions, and positive ions are only formed if an electron is removed. We are then asked to explain why the charged ions accelerate towards the collector electrode. Well, you can say that they accelerate because they experience a force due to the electric field. You can also say that the positive ions are attracted to the negative electrode. Either answer would be accepted. In the next part, we're told the potential difference between an electrode is 1 kilovolts. Assuming that the field between the electrodes is uniform and the charge on each ion is 1.6 times 10 to the negative 19 coulombs, calculate the work done in moving one ion from in between the electrodes. So we're just using the equation we used before in electric fields. W is equal to QV, which is 1.6 times 10 to the negative 19 from the question, multiplied by 1000, again, given in the question. Gives us a value of the work done to be 1.6 times 10 to the negative 16 joules. Calculating how many ions are created each second requires just a little bit of extra thought. Got to think back to National 5. P is equal to E over T. Because we're told in the equation that the power is equivalent to 0.1 watts. So P is equal to 0.1 watts. So 0.1 is equal to the energy per unit time. Time being each second, meaning the energy is 0.1 joules. So we know the total amount of energy that's supplied. We know the work done in moving a single charge. In order to find the number of charges, we've got to look at the total energy divided by the work done per charge, which is 0.1 divided by 1.6 times 10 to the negative 16 joules. You end up with a value of 6.25 times 10 to the 14. No units. That's the number of ions. In the last part, we're asked to explain how the device calls a microprocessor. Well, if you remember, the positively charged ions are attracted to the negative electrode. And as they move left to right, they're colliding with the neutral air particles. As they collide, the momentum is transferred from the positively charged ion to the neutral air atoms. So the flow of air current and that's the flow of the moving neutral air atoms removes energy from the chip. So those neutral air atoms are absorbing some of the heat energy from the chip. Positive ion, which is being accelerated, collides with the air particles, moving them along. So you're moving the warm particles, the warm air particles, away from the chip, only to be replaced by cool air particles, which then absorb a little bit more heat. And that movement of the particles causes heat to be continually removed from the chip, thus cooling the microprocessor down. Okay, so here's an open-ended question. So this would be 3 marks, 2 of which are A-type. The sun is constantly ejecting positive and negatively charged particles at very high speed. This flow of charged particles is called the solar wind. The charged particles can cause significant damage to life and also to electrical equipment if they reach the surface of the Earth. We are protected from the charged particles by a field. This field is produced by the Earth and deflects the solar wind. Use your knowledge of physics, explain whether the protecting field is electric, magnetic, or gravitational. So you can pause the video here and have a shot yourself, and then on the next part, you'll give some points towards a possible answer. But please remember, for 3 marks in an open-ended question, you're not looking for a perfect answer or a complete answer. You're looking for something which shows a good understanding of physics. So if you had any 3 of the points on the next part of the video, then you would be getting the 3 marks. But we're looking for them to be connected together to show your understanding. So possible answers to this question. Well, first of all, the field around the Earth is a magnetic field. So that's going to give you a point because you're showing that you're understanding. You're answering the questions being asked. When the charged particles interact with a magnetic field, they experience a force. That force is perpendicular to the flow of the charges. That's the left-hand rule, right-hand rule. The direction can either be up or down depending on whether the charge is positive or negative. As the solar wind is made up of both positive and negative charges, this means there will be forces going both up and down. And that's why we have the aurora and in both the south and the north poles. But there are also other answers you could add onto here. These are just some potential answers. The only one that's really key is you mentioning that the field is magnetic, because that is specifically asked within the question. And then in order to get the other 2 marks, you simply need to show some understanding of the interaction between charged particles and a magnetic field.